All right, we're going to talk about the self-bias configuration for the junction field effect transistor. Here's the schematic configuration for the Jfet self-bias circuit. So hopefully you're already a little familiar with Jfets. This page, I'm basically bulleting out all the things that I think are very important for you to know and understand concerning Jfets. So there's basically two ways to analyze these Jfet circuits, bias circuits. We're going to look at them, the graphical method and the quadratic method. So we're going to start out first by looking at the graphical method. And what we need to do first is we've got a formula, ID is equal to IDSS times quantity 1 minus VGS divided by VGS off, that squared. Right there, kind of 2 bullets down. And we want to use this formula to develop the characteristic curve of the actual device, the Jfet. And this basically shows you the steps. So you're going to plot through, you've got VGS as your x-axis. It's going the other way now because VGS is negative with respect to VRS. And so the graph is now turning and going the other direction compared to what we were used to for BJTs. And the vertical axis, or the y-axis, is the drain current, the current in the drain, which is also the same as the current in the source. And IDSS is that max device current. So we're going to punch through, and we're going to start, I start with 0 for VGS, run through there. It should pop out your IDSS if you put 0 for VGS. And then move your way all the way to VGS off. So you've got VGS off over VGS off in the formula, and that should give you 0 drain current. And of course, the more data points that you plot, the better resolution you'll get on your characteristic curve. Once we've got our characteristic curve developed, we can now plot our circuit across that curve. And essentially, it's our RS across that curve. And the way to do this is to write a Kirchhoff loop equation. And I'm starting at the, I guess, the bottom of RG, and I'm going to say minus RG plus or minus VGS plus VRS should equal 0. And we know for these Jfets that there's very little gate current. These are voltage controlled devices, and there's very, very small, so small that we can not even calculate, or we can assume 0. And so we know if there's 0 gate voltage, then we've got 0 VRG. So that just drops away in the formula, and now we end up with VRS is equal to VGS. And now that we know that VRS is equal to VGS, we can plot that across our characteristic curve. And so what really all we're doing is we're saying, well, if VRS is equal to VGS, then I could say, well, 0 VGS, 0 volts divided by RS should be a 0 ID, no ID in the equation, and just march that across and all the way to VGS off and calculate what the ID would be and plot that straight line. And as we develop the line across, you'll see it starts right in the corner because we're starting at 0 volts and 0 ID. For the circuit, you can see where basically the circuit now crosses the characteristic curve, and that is where we're going to be operating for your circuit. That's going to be your circuit ID and your circuit VGS. So the more careful we are about calculating the curve and developing the circuit line, or the RS, across the curve, the more accurate we'll be at being able to look at that dot and determine what the actual ID and VGS are. And for me, I usually do the graphical analysis first, and I'll write down what the ID and VGS are approximately, and then I'll switch to the quadratic analysis to verify. So for the quadratic analysis, we're going to go back to our ID formula, and we're going to write a Kirchhoff loop just like we did before and establish that VGS is in fact equal to VRS. And now we know that VRS is also equal to ID times RS. And so we can substitute the ID times RS into the original ID formula. Because the problem was we had too many variables and we're trying to solve for ID. And so we know what RS is in our circuit. And now we know what IDSS. We should know what IDSS is. We should know what VGS off is as well. And now we've got everything in terms of ID. Okay, so now you're going to do a bunch of math. The one things I need to point out is for the ID times RS, the numerator of that section, we've got that over VGS off. If we had originally solved for a negative VGS, we would want to put a negative VGS off in the denominator. So VGS and VGS off are both going in the same direction, so they both have the same polarity. So it's real important to, whatever you do, make sure you do the same in the numerator and the same in the denominator, because if you flip the polarity of one, it'll kind of goof you all up. The other thing is we're trying to get to this ax squared plus bx plus c format, and so the other thing that people will sometimes miss is when you do all your final equation, you have ID equals all this stuff on the right. Well, that ID that's sitting there is a 1 ID. And so you need to subtract that off because you really need 0 on the one side of the equation. So it's got to be 0 on one side of the equation, and then you've got your ID squared, your ID, and your C value, and now we can use the quadratic equation to solve for our ID. The other thing to point out here is for the quadratic equation, usually it's minus b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. To solve for our ID current, our drain current, we only need to do the minus instead of the plus or minus. We're just going to use the minus, and that should give us our ID. Now, once you've got your final solution using the quadratic method, we're going to compare that ID value to our graphical method. And as long as those line up, if those line up, then we know we did all of our math right. We've got the drain current for the biasing circuit correct. So as always, we need to check our biasing circuit at the very end by developing a DC load line. And for this circuit, if we treat the transistor as a open switch, that would be our VDS cutoff. And if it's an open switch in series with these other two resistors, we would expect to see all of VDD as our cutoff voltage. And if it was a closed switch, that would be our saturation current. And if it was closed switch, we'd expect all of the VDD voltage to be dropped across RD and RS, and that would determine our max current. Now, another thing to point out here is our ID sat needs to be below our IDSS, which is the specification for the device. So if your IDSS is like 10 milliamps, for example, you would want your ID sat to be around like 8 milliamps, something less than 10 milliamps. Because if your ID sat was set at 11 milliamps, you would never get to your saturation current. It would bottom out at 10 milliamps, the IDSS. So you want your saturation current to be below your IDSS. And then finally, we need to check our VDS and our ID and make sure, hopefully, it's somewhere in the center of the active load line.